What's up everyone, and thank you for choosing to learn with LAM. Today we're going to be going over Hess's Law and making sure we have a good feel for the types of manipulations that we can use. First things first, Hess's Law states that the enthalpy change of a process is dependent only on the initial and final conditions of the process. What this means is that as long as your starting material, so your reactants, are the same, and your ending materials, so your products, are the same, the amount of energy absorbed or released, or the enthalpy, will be the same, regardless of the types of reactions that occur or the number of steps involved. So let's jump right into a problem here and we can take a better look at what we mean. Say we've got the formation of nitrous acid here. So half a hydrogen gas plus half a nitrogen gas plus oxygen gas makes HNO2 aqueous. And I want to know what the enthalpy of that reaction is. In a typical Hess's Law question, you'll be given multiple other reactions that can be manipulated such that they can add up and provide you with the original reaction that you're looking for. You'll also be provided with each of their enthalpies. So let me just write those down for you real quick. Now, it's important to understand that each of these numbered reactions are not necessarily steps in the formation of nitrous acid. They're just separate reactions that in combination can have the same reactants and products as our formation reaction. Alright, so what we're trying to do here is arrange the numbered reactions so that we have the correct number of particles in the correct places, like the way it's shown in our desired reaction. Now, the way I like to approach these problems is to identify the substances in my desired reaction that only show up once in the numbered reactions. For example, we have nitrous acid in our products here, and it only shows up once down here in reaction 2. This means that reaction 2 is the only opportunity that we have to put nitrous acid in the correct place with the correct coefficient. Compare this to trying to work with nitrogen. The issue here is that we've got nitrogen in reactions 1 and 3. Now, even if we manipulate reaction 1 to set up nitrogen the way that we want, as soon as we manipulate reaction 3, that's going to affect nitrogen as well, and it's going to change whatever we did originally. So we're going to stay away from those guys and leave them for later. Alright, so back to HNO2. I want one HNO2 in the products. Now, in reaction 2, we've got one HNO2, but it's on the reactant side. So what do? What we're going to do is turn the equation around, just reverse it. But remember that when we do that, enthalpy changes sign. If a reaction releases energy going in one direction, it will absorb the same amount of energy going in the reverse direction. So to show that we're reversing a reaction, we're going to multiply it by -1. So we'll rewrite reaction 2 with the manipulation that we want down here. We flip the reactants and products, and most importantly, we also multiply the enthalpy by -1, meaning the new enthalpy for this reaction is positive 37.7 kilojoules. Now, notice that we end up with ammonium nitrite in our reactants, and that's not in our desired reaction, but don't worry, we're going to take care of that later. Alright, next equation that we want to work with is reaction 4, because it's the only place we can manipulate oxygen. Notice that we need oxygen as a reactant, and reaction 4 has it as a reactant. However, we need 1 oxygen, and reaction 4 only has half. No problem. We don't need to flip this equation, but we're going to multiply the whole thing by 2, including the enthalpy. So now we've got 2 hydrogen gas plus 1 oxygen gas, making 2 water, and our enthalpy is now doubled at -571.6 kilojoules. Alright, now we're out of our for sure reactions, but because we've already locked in reactions 2 and 4, we can now use 1 and 3 to make any adjustments that need to be made. For example, that ammonium nitrite that we had mentioned earlier. Because reaction 2 is locked in, reaction 1 is now the only other opportunity we have left to get rid of that ammonium nitrite. Right now, we've got ammonium nitrite as a reactant in reaction 2, but if we reverse reaction 1, then we'll also have ammonium nitrite in the products, and they'll cancel out just like spectator ions do in net ionic equations. So let's reverse reaction 1, and don't forget to multiply the enthalpy by -1 also. Once that's done, we can cancel out the ammonium nitrite so that we don't have to worry about it anymore. Alright, only one reaction left here, and we can see that we have ammonia here that I want to get rid of. Luckily for us, there's an ammonia in reaction 3. Considering we have ammonia in our products and we want to cancel it out, it's good that reaction 3 has ammonia as a reactant. However, reaction 3 has 2 ammonia and we only need to cancel out 1. So we're going to multiply reaction 3 by half or divide it by 2, however you prefer to think of it, and that will give us the final piece to our puzzle. And of course, don't forget to multiply the enthalpy as well. And now we can cancel out our ammonia. The nice thing about Hess's Law questions is that they always work themselves out in the end as long as you go through the reactions in an order where there's only one option for manipulations, as we've been doing. Notice here that the waters just conveniently cancel themselves out. And even though we have a bunch of nitrogens and hydrogens floating around, we can be very confident that we've made the correct manipulations because we really didn't have any other options. Still, it's always good to double check your work, so let's add up all of our reactions and make sure we get the correct desired reaction. Alright, so in total I have 2 hydrogen gas plus nitrogen gas plus oxygen gas, and that makes nitrous acid plus half nitrogen gas plus 3/2 hydrogen gas. Now, notice we've got hydrogen gas on both sides of my equations. We're still going to cancel them out, but they won't cancel out completely. If I cancel out 3/2 of hydrogen on both sides, that still leaves me with 1/2 hydrogen in my reactants. Similarly, for nitrogen, if I cancel out half a nitrogen on both sides, that leaves me with half a nitrogen in my reactants. But that's actually perfect, since that's what we needed for our desired reaction anyway. Alright, now that we know that our manipulations are correct, we can just add up all of our enthalpies, which will give us the total enthalpy for our desired reaction. And that totals negative 128.85 kilojoules. And that's all there is to it. As always, if you have any questions or if you have topics you want me to cover, just leave them in the comments below. Good job, everyone. If you find that you need a little extra help, please feel free to check out my other videos for tips and tricks on how to succeed in school. And as always, thanks for learning with LAM.